Okay, now we move to the next topic, 2.2, the equation of motion. And here we will look four parts. The first one is the system of particles, rectangular coordinates, normal and tangential coordinates. Last one is the cylindrical coordinates. Okay, as we know, kinetic is a branch of dynamics that deals with the relationship between the change in motion of a body and the force that causes this change. The basic for kinetics is Newton's second law, which states that when an unbalanced force acts on a particle, the particle will accelerate in the direction of the force with a magnitude that is proportional to the force. This law can be verified experimentally by applying a known unbalanced force F to a particle and then measuring the acceleration A. Since the force and acceleration are directly proportional, the constant of proportionality m may be determined from the ratio of m equal to F over A. This positive scalar m is called the mass of the particle. Being constant during any acceleration, m provides a quantitative measure of resistance of the particle to a change in its velocity that is its inertia. We will talk more on the inertia as we go further into these courses. Okay, if the mass of the particle is m, Newton's second law of motion may be written in mathematical form as here, m is equal to ma. Okay, now, F equal to ma, just like that. From the Newton law of gravitational attraction, shortly after the formulating this, Newton postulated a law governing the mutual attraction between any two particles in the mathematical form can be expressed as like so. Okay, and each of the variables here is mentioned down here. Okay, this is two. Okay, on the left here we have the SI unit, and it is from the US unit. Okay. Okay, the free body and the kinetic diagram for the ith particle are shown in figure 13 for B. Okay, here. Okay. Applying the equation of motion, the summation of F equal to ma, or you can write it in a more complete. Okay, we have capital F, the small f. Okay, summation of this should be equal to this one, and then we have mi and ai. Okay, when the equation of motion is applied to each of the other particles of the system, similar equations will result. And if all these equations are added together vectorially, we obtain like so. Okay, this is the coordinate or the reference axis like, as we have discussed before. Okay, anything that you are going to analyze, you should have a reference axis or reference frame. Okay, then much easier for you to define the orientation or the applied force that acting on a particular particles. Speaking about the initial reference frame, when you apply the equation of motion, it is important that the acceleration of a particle be measured with respect to the to a reference frame that is either fixed or translate with a constant velocity, like what we have on the left here. In this way, the observer, this guy here at point O, will not accelerate, and measurement of the particle's acceleration will be the same from any reference of this type. Such a frame of reference is commonly known as a Newtonian or initial reference frame. When studying the motion of rocket and satellite, it is justifiable to consider the initial reference frame as fixed to the stars, whereas dynamic problems concerned with motion on or near the surface of the Earth may be solved by using an initial frame which is assumed fixed to the Earth. Even though the Earth both rotates on its own axis and revolve about the Sun, the acceleration created by this rotation are relatively small, and so they can be neglected for most applications. Now we jump into the rectangular coordinates. When a particle moves relative to an initial x, y, z frame of reference, the force acting on a particle as well as the acceleration can be expressed in the I, J, K component like what we have here. Okay. Then you can further look at it one by one. One by one means in the x direction, y direction, and z direction, like so. Okay, now we look into one example. There is a crate or a box here. Okay, it is weight 50 kg. Okay, it is a 50 kg on a horizontal surface, and the kinetic friction acting on this particular crate is equal to 0.3. If the crate is subjected to 400 Newton, this one, towing to the right, okay, determine the velocity of the crate in 3 seconds, starting from rest, which means that initially it is at rest. Okay, so now jump to here. So again, before you proceed with any analysis, please define your reference axis, okay, like so. Then from there, okay, draw your object, okay, from one particular view that is the most appropriate view, okay. In this case, the view from this side. Okay, then you draw all the forces involved, including this friction here, Ff. I normally put it as Ff. Okay, friction force, this one. And C is the normal force acting between this particular surface. And this is the weight, which is mg of this. M is given 50 kg. So now we solve in the both direction, in the x and in the y direction. Okay, remember this is the kinetic problem, and we know that this particular problem, okay, will only have motion in the x direction. Okay, and here we have the ax still there, but in this case doesn't have anything to do in the y direction, so this becomes 0, and therefore you can see it is equal to 0. Okay, then if we look back into this summation of fx, what we have in the fx is we have fx should be this one. Okay, so 400 cosine 30 degrees minus 0.3 NC. Okay, this part here, because because the direction is on to the left. So that's why you have the minus sign. And for the y-axis, okay, y-axis, what we have this W, we have this NC, we have this, and we also have this Y component of this 400 Newton. Okay, we have 1, 2, and 3. Okay, that's all parts. Then you have two equation and two unknowns, which is NC and A. Therefore, you can solve for each of them. Okay, and nothing that since you want to calculate the problem would like to find out the velocity of the crate in 3 seconds starting from rest. So you can use this kinetic equation like we have learned in the first chapter. Okay, like so. So this is your answer. Moving on. Okay, similarly, we look into this projectile fired upwards. On the ground, initial velocity is 50, and we need to determine the maximum height to which it will travel. Okay, now in this case, there are two conditions. On the A, on the first part, the atmospheric resistance is neglected, which means that there is nothing to slow down this motion of this projectile, no drag involved. However, for B, there is atmospheric resistance and therefore there is a drag force. Drag force we denote as Fd, 0.01 v square. It's function of velocity. Okay, which means here you can see from this equation, when the v is become bigger, then the drag is also become way much bigger. Okay, and on the left, similar to the previous problem, we look into the x and y component. On this case, use z as the upward. Okay, that is the direction of z. Okay, that is totally up to your preference. If you want to use y, therefore here the subscript here you need to change to y. No issues. Okay, then you need to use the Newton's second law. Okay, find this value of a. Then use this from the knowledge of kinematics to find out the maximum height. Okay, the maximum height that this projectile can reach. Okay, on the right hand side, okay, what we can see here, the component of drag is also included, okay, into this equation. Therefore, you will have this equation for A, and then you solve it into the you do the maths, okay, to get this to get it in the with a function of v, and then you resolve it to get this. Is actually, if you notice, is the same like before, where we have a ds equal to v dv. Okay, okay, separating the variables and integrating, realizing that z is equal to 0, then v naught equal to 50 meter per second upwards, then you can do the integration, and then you get this value of h, which is equal to 114 meter. And notice that this value is slightly lower compared to this one. Okay, because of there is element of drag that slow down this, that resists the motion. Okay. Okay, moving on to the third one, normal and tangential coordinate. Newton's second law, okay, again, summation of F equal to MA. For tangential and normal component, we have Ft equal to MAT. And then if you further expand on this part, you'll get something like this. Okay, that is for the tangential part. For the normal component, for AN, as we have discussed previously in the first chapter, that this component AN here, you can expand and become V square over rho. Okay, like so. Okay, on this particular problem, the bob of a 2-meter pendulum describes an arc of a circle in a vertical plane. If the tension in the cord is 2.5 times the weight of the bob for the position shown, find the velocity and acceleration of the bob in that position. The bob is this one. We call it bob. Okay. Okay, first you need to resolve the equation of motion as usual for the bob. Resolve it into the tangential and normal components of the component equation for the normal and tangential acceleration. Okay, what is the difference between the previous part where we resolve in the x and y axis, right? But in this case, we resolve it into the tangential and normal component. Okay, okay. Also into the two component. Okay, then solve for velocity in terms of normal acceleration. Okay, here you can see this is your free body diagram for this part, this bob here. Then solve for the component equation for the normal and tangential acceleration. Okay. And then you resolve the this is the tangent part, okay, and then solve for the normal part for this acceleration. And then solve for the velocity in terms of the normal and acceleration. Okay, that's all. Okay, moving on. Here we have a car, and on this particular problem, we need to determine the rated speed of a highway curve of a radius 120 meter bank through an angle of 80 degrees. Okay. Sometimes if you watch NASCAR, for example, NASCAR or test circuit, okay, normally at the corner or at the curve, they will have a slight incline or bank angle, okay, to actually prevent or to improve the ability of the car uh, improve the ability of the car to enter that particular corner at much higher speed, okay, to prevent skidding. Okay, to okay, the car travel in the horizontal circular path with a normal component of acceleration directed towards the center of the path. The forces acting on the car are its weight and a normal reaction from the road surface. Okay. Then you resolve the equation of motion for the car into the vertical and normal component. Then resolve in the first in the Fy, and then in the normal component of it. Okay. Okay, the last part, uh, we want to look into the EQS, stand for equation of motions. Okay, equation of motion. This equation of motion in radial and transverse component. Consider particle at r and theta in polar coordinates. Okay, this part here, sorry, this part is actually the same thing that we already discussed earlier. Okay, I put the link down here. I didn't put the link. I put the description down here that to highlight that what we have discussed before on to derive this particular equation. Okay, this one. Okay, this part and also this part. Okay, one for the R, which is this, and this one for this. Okay. Okay, now we have one problem. There is a 3 kg collar. This one slides on the frictionless arm AA prime. Okay, this collar here will slide in this collar AA. The arm is attached to a drum. Okay, this is drum and rotates about point O. Okay, this particular arm here will rotates horizontal plane at the rate of 0.75 t, where theta dot, or the rate of rotation and the time are expressed in radian per second and seconds respectively. As the arm drum assembly rotates, this one rotates, the mechanism within the drum release the cord so that the collar move outwards from O. Okay, this one rotates. Okay, I presume counterclockwise, then this will go over there, be going up at the speed of 0.5 meter per second, knowing that at t equal to 0, r is equal to 0. Determine the time at which the tension in the cord is equal to the magnitude of the horizontal force exerted on B by arm AA prime. Okay, first we need to draw the free body diagram and the kinetic diagram for the collar. Write the equation of motion for the collar. Determine kinematics of the collar. Then combine the equation of motion with kinematics relationship and solve it. Okay, this is the process. We are given that the theta dot is equal to 0.75 t when r at t equal to 0, r also equal to 0, r dot is equal to 5 meter per second, and we need to find when t equal to n. Draw the free body diagram. Free body diagram is more or less like this. Okay, write the equation of motion like so. This is your equation of motion. Okay. Then find the expression for r and theta. Substitute values into AR and A theta. So substitute into equation of motion. Okay. Set t equal to n. Then, and that's all. Thank you.